I'm Seigo TARUCHA from RIKEN. So it's a great pleasure to talk about our Moonshot project. We already had a very nice talk by two world-leading scientists in our community, so I can forget all of the explanation about the background. So I will jump in. We have 5 PIs, Takashi Nakajima, RIKEN, Takafumi Fujita, Osaka University, Satoru Miyamoto, Nagoya University, and Michihisa Yamamoto, RIKEN, and Tokyo University, and Shintaro Takada, ICE, Advanced Institute for Science and Technology. So then, our milestones are to build the technology basis of implementing scalable multi-qubit devices, hopefully in collaboration with the semiconductor industries, and also demonstrate the proof of a quantum error correction optimized for semiconductor quantum computing. There are several challenges we have to sort out before we reach this goal. The first is scale up. This is a big topic. So we are making building blocks of qubit layout and the middle distance quantum link to connect to quantum registers or quantum processors by shuttling mechanism. And the second is the substrate quality and the Valley problem in silicon. So then our PI is working to control the interface step in a large area isotopically purified silicon germanium. Third is the error correction, which must be an optimized error correction for a biased noise, where the T1 time is much, much longer than T2 star. And then this will be done, we expect, in collaboration with our Moonshot theory project. And the fourth is wiring. This includes the problems of multi-layer interconnection, 3D wiring, integration with the cryoelectronics. This we hope to do in collaboration with industry and the Moonshot experiment project. And some others include the fridges, auto-tuning, cost, manpower, and so on and so on. So depending on the time, we are interested in working on these topics as well. And then in a project, I will present as an alternative approach to save the cost of resources using a concept of flying qubits of electron wave packets. Okay, so then Takashi Nakajima, RIKEN, is working on the development of scalable technologies for fault-tolerant silicon spin qubits. And the Takafumi Fujita working on the development on middle distance quantum link. And Satoru Miyamoto working on the development of isotopically controlled silicon germanium substrate technology. And Yamamoto and Takada are both working on development of electron wave packet qubits with a new principle. Okay, so then our project started just 10 months ago. So I will mainly explain you the outline of the project and some small progresses. So then many of the PIs have made their own efforts to install, for the moment, the large-scale facilities, big dilution fridges, electronics, crystal growth equipment. Hopefully, it will be done in end of 2023 this year through beginning of 2024. Experimentalists cannot do anything at all without the experimental setup. So then we have some progresses in the program. Takashi Nakajima is developing a multi-qubit device prototypes, including 4 to 10 qubits, and improving the qubit control technology as well. And the Takafumi Fujita is fabricating quantum dot arrays for a qubit transport channel, which is discussed by RIKEN, and Satoru Miyamoto is designing the silicon-germanium interface control technology, which is related to the valley degeneracy problem. And Michihisa Yamamoto and Shintaro Takada are both working on developing a generation and control technology of wave packet propagation as qubits. Okay, so then I will explain you about the progress or the program outline for the respective PIs. First is the Takashi Nakajima. So the development of a scale-up technology is the most important issue. And 2 years ago, we fabricated the 3 quantum dots and operated 3 qubits with high fidelity. And just last year, TU Delft and Lieben's group fabricated the 6 qubits also with high fidelity. And more recently, Intel announced that they have fabricated the 12-qubit devices, which is so-called a tunnel fold device. And the approach to scale up these qubit systems is one way is to make a 2D qubit array. We have actually proposed a model of 40 by 40 qubit arrays. And the other way is to make a network of qubits or quantum registers. And then our approach is to scale up the qubit system by interconnecting one-dimensional qubit arrays. The necessary requirement here is the device structure allowing for a qubit initialization, readout, and application of microwaves and gate pulses, and wiring to dense gate electrodes around the devices, and demonstration of basic error correction code. And then first, I will explain about their progress on the quantum network systems. To interconnect the qubit arrays and not only the shuttling, but also a 2-qubit gate between distant quantum qubits should be implemented. This is also based on the spin shuttling technique. So then we used a triple quantum dot to examine the coherent spin shuttling and 2-qubit gate with the non-neighboring qubits, and then obtained the coherence fidelity of spin shuttling of 99.6%. This is just one dot shuttling, not the case for Lieben's multiple quantum dots. And we obtained the shuttling-based control phase gate with a fidelity of 93%. We are improving of these values. And just before the project started, we have demonstrated the quantum error correction in the preliminary stage using 3 qubits in the repetition code. And they show that the phase error is well corrected for if the error occurs on a single spin. So then in this experiment, we use a I-Toffoli gate to detect and correct the phase errors. And then this works to shorten the error correction overall time down to 700 nanoseconds, which is significantly shorter than the dephasing time. This is good for using the Toffoli gate, but not good for the larger cores. We need to do a measurement-based collection. So then the measurement must be fast enough, and also high fidelity is required. And then we optimize the spin readout technique, and also measure the parity selection measurement, and also the latch readout. And obtain the fidelity of 99% for the state preparation and measurement with integration time of 0.5 microsecond, which is not so good as the value Michel obtained, but it may be good enough for the quantum error correction circuit. Okay, we also worked to improve the state preparation technique to get the high fidelity, and we used the repeated quantum non-demolition measurement to prepare a reset pulse, well-defined, and then made an active reset of the data qubit using an ancillary qubit. And then we achieved the 99% initialization fidelity with repeated measurements and active reset. And we also developed some error analysis method using a gate set tomography for high fidelity 2-qubit gates. We analyzed the error sources, for example, the C0 error for the various two sets of quantum operations. And here in this set, the main error source comes from the IX and ZX operations. We did some compensation pulse and reduced the two errors very much. And then we find that this technique works to get the 99.4% 2-qubit error by preparing inappropriate gate pulses. Okay. And then for the coming years, Nakajima's team is designing and fabricating and characterizing building blocks of sparse qubit structures. These are the building blocks we are considering, and they will start high-fidelity qubit control experiments using more than 4 qubits. Okay, next is about the team of Takafumi Fujita, and we have previously demonstrated the shuttling of quantum bits and also 2-qubit gate operations. The one is done by Takafumi Fujita himself when he was in TU Delft, and also the other is done by Akito Noiri at RIKEN. And then his task is to develop a quantum link using a one-dimensional quantum dot arrays. So then 1D qubit arrays can be interconnected quantum mechanically. And it should work to scale up the qubit devices. And then for the moment, they are preparing the overlapping gate electrodes for making 1D quantum dot arrays in a stable manner. And then they simulated the potential to transfer the qubit through the 5 quantum dots. This is a simulation of a potential dynamics in the so-called the conveyor mode. And they are also doing some calculation of the time-dependent potential and wave functions for the conveyor mode and also adiabatic spin chain. Okay, and for the coming years, they are increasing the number of quantum dots here up to, I think, up to 10 of them. 25 or something. Just for fabrication. And they are now testing very much the qubit transfer using a 5 quantum dot device. But the technology should be extended to more than 10 quantum dots. And this is prepared using gallium arsenide quantum dots. Then they are finally transfer the technology from gallium arsenide to silicon. Okay, next is the team of Satoru Miyamoto. He's a crystal grower, and he has a good experience of growing the isotopically purified silicon in Keio University. And then their topic is to implement the large-scale silicon quantum platform to satisfy the requirements of fault-tolerance quantum operations. And by implementing the high-quality isotopically purified silicon germanium crystal. And also the atomic scale interface control technology to solve the Valley degeneracy problems. The Valley degeneracy, as mentioned by RIKEN, is a serious, sometimes, not always, but sometimes a serious problem when you make many devices. So if the one device has a very small spin Valley splitting, the dephasing occurs very quickly, and this must be sorted out. But when you think about the mechanism of the Valley splitting, it will be reduced when you can make a large area flat terrace, atomic terrace, at the interface of silicon and silicon germanium. So then to control this kind of step and the terrace at the interface is a key point. So then they have 3 minutes. Sorry, they have an approach using a hydrogen incorporation at the interface to control to break the atomic bond and control the strain, which should work to control the atomic step at the header interface. So they are now working on that direction for the coming years. Sorry, I do not have much time. So Michihisa Yamamoto and Shintaro Takada are both working on the flying qubits of electron wave packets to construct a new concept, the quantum computer. And they are considering this kind of a loop channel for electron wave packets traveling. And then electron propagation can be assumed to be flying qubits. And this short pulse does not decay for over a millimeter scale. So then they can accommodate the number of qubits, and this helps the too much resource effect in the fix the quantum qubits. Okay, and they have already observed the suppression of the coherence for injected short electrical pulses, and they have realized a scalable two-path interferometer consisting of only one transmission channel with a strong Coulomb interaction. And recently, they succeeded in tuning the plasmon velocity by local gates. And then the progress is listed here. They developed the highly controllable quantum circuit consisting of a single channel and investigated the Coulomb interaction effects between electrons in the circuit to control the two-qubit gate effect. And they developed a new method to control the velocity of electron wave packets. Okay, for the coming years, they are interested in, motivated to to verify their concepts by generating an ultra-short electron wave packet by converting light pulse to electric pulses, and realize high fidelity quantum operation using those flying qubits, and demonstrate actually the long coherence of a time-being qubit of an electron wave packet. And then also they are working to develop a readout technique of a single wave packet using a spin qubit technique. Okay, now depending on now coming back to the silicon, so depending on the number of qubits, you need to develop some different technologies or upgrade your technologies, maybe up to 100 to 1,000, just a brute force by expanding your current technology. This should work for wiring at the device level, control electronics and wiring on high frequency lines, but the new technology must be incorporated for the qubits more than 1,000. This must be the case also for the cryo system. To prepare a very large dilution fridges is one way, but there must be some limitation. We cannot couple so many number of the dilution fridges. But advantage of silicon is that the silicon qubits work above 1 Kelvin. So then we do not need the dilution fridges. We can only prepare a 4K fridge, which gives 1 to 2 Kelvin with the power of 100 watts. So it's 2 or 3 orders of magnitude large, which is expected to be good for 100,000 qubits in my optimistic calculation. So this is the summary of our project, but the time is running out. I just place this slide here. So thank you very much.